Imagine drifting through space, not near a star or a planet or even a distant galaxy. Just nothing. No light, no warmth, no sound. Only darkness. Endless, unbroken, suffocating darkness. If you could travel far enough, beyond the galaxies that dot our night sky, beyond even the clusters that group them together, you'd eventually find yourself in a region so vast, so empty, it defies imagination. These are the cosmic voids, the true dark spaces of the universe. Most people imagine the universe as full of stars, planets, nebulae, and galaxies. But the truth is far more haunting. Almost everything we can see, every star, every world, every galaxy, is confined to a thin web of light stretched across an infinite cosmic skeleton. And between the glowing strands of this web lie immense regions of emptiness, voids that make up most of existence itself. If the universe were a city, galaxies would be its shimmering buildings, and the voids the silent streets between them. But in this cosmic city, the streets are millions of light-years wide. Let's start with a simple fact. About 80% of the observable universe is empty space. These voids aren't small gaps. They are colossal bubbles, each spanning hundreds of millions of light-years. The nearest major one to us, known as the local void, begins just beyond the Virgo supercluster, the cosmic neighborhood our own Milky Way belongs to. In these places, the night sky would look completely alien. There are no nearby stars to light your surroundings. The faint glow of galaxies might be visible on the far horizon, like distant lanterns flickering at the edge of perception. But around you, there would be only silence. A silence that stretches for eternity. Yet this emptiness isn't meaningless. In fact, it's essential. Without the cosmic voids, the universe as we know it could never have formed. Let's rewind the clock, all the way back to the beginning of time. Right after the Big Bang, the universe was hot, dense, and almost perfectly uniform. A smooth sea of energy and matter. But almost is the key word, because in that smoothness, tiny fluctuations, slight differences in density appeared. Some areas had just a little more matter than others. Over billions of years, gravity pulled those slightly denser regions together, forming stars, galaxies, and clusters. The underdense regions, where there was a bit less matter, were stretched apart, expanding faster, emptying out. Those underdense regions became today's cosmic voids. If we could zoom out far enough, not just beyond our galaxy, but beyond entire clusters of galaxies, the universe would look like a vast three-dimensional web. Scientists call it the cosmic web. The bright filaments are where matter clumped together, galaxies, stars, and light. The dark regions between, those are the voids, immense cosmic bubbles where gravity has swept almost everything away. It's strange to think that most of the universe is made of nothing. We look at the night sky and feel small because of how vast it seems. But the truth is, what we're seeing is only the glittering surface of a much deeper ocean of darkness. And yet, these voids aren't completely empty. Every so often, within their infinite darkness, you might find a lonely galaxy, drifting, isolated, light years away from any neighbor. These galaxies are like cosmic castaways, trapped in an endless sea of nothingness. Astronomers call them void galaxies. They're rare, faint, and difficult to study, but their very existence is a clue, because understanding why they're there and why most matter avoids the voids helps us understand something profound: how structure itself forms in the universe. In 1981, a team of astronomers led by Gregory and Thomson discovered the first large cosmic void while mapping galaxy positions in the sky. They found a huge empty patch, nearly 200 million light-years across, with almost no galaxies inside it. This discovery changed everything. It revealed that the universe isn't uniform, but patterned, shaped by an invisible tension between matter and nothingness. Today, with powerful 3D maps from telescopes like the Sloan Digital Sky Survey, we can see these voids in extraordinary detail. They're not random gaps, they form an intricate network, like the bubbles in a foam. Each void is surrounded by walls of galaxies, clusters, and filaments, the visible scaffolding of the universe. And just like bubbles in a soap foam, the voids press against each other, defining the structure of everything else. So the next time you look up at the night sky, remember this. What you see, all the light, all the beauty, is only the thin surface of reality. Behind it lies an ocean of darkness, silent, infinite, and waiting to be understood. The invisible architect. When most people imagine a black hole, they picture a cosmic vacuum cleaner, a monstrous pit that swallows everything around it. But that's not quite right. A black hole doesn't pull things in like a mouth devouring its meal. It bends space itself, creating a slope so deep that anything too close simply can't climb out. Imagine space not as emptiness, but as a flexible sheet, like a trampoline. Place a bowling ball in the center and the surface curves. Now roll a marble near it. The marble doesn't fall in because the bowling ball sucked it, but because the curved surface directs its path. A black hole is the ultimate bowling ball, so massive, its weight doesn't just bend the fabric of space. It tears it open. What's fascinating is how invisible this cosmic sculptor truly is. The black hole itself emits no light. We only know it's there because of how it shapes the behavior of everything around it. Light, gas, stars, even time itself. When matter spirals toward it, friction heats it up to millions of degrees, creating a glowing disk known as the accretion disk. It's that fiery halo that gives the black hole away, the light before the plunge into silence. But even that light tells only part of the story. Beyond it, near the event horizon, time begins to twist in strange ways. For someone watching from far away, anything falling toward the black hole seems to slow down, stretch, and fade, frozen just above the edge. But for the falling traveler, time feels normal. They cross the boundary in an instant, never realizing that the universe outside has aged beyond measure. It's one of the most haunting ideas in physics. The same moment seen differently depending on where you stand in the cosmos. To understand how black holes warp reality so profoundly, we need to talk about gravity, not as a force but as a geometry. This was Einstein's greatest revelation. In his general theory of relativity, gravity isn't an invisible pull between objects. It's the shape of spacetime itself. Massive bodies like stars curve this fabric, and that curvature tells everything else how to move. Black holes are where this curvature becomes infinite, where the map of spacetime folds in on itself so tightly that all paths point inward. Every road, every direction, leads to the same destination, the singularity. And what is the singularity? It's the heart of the black hole, a place where our understanding of physics collapses. Here, matter is crushed to an infinitesimal point, density becomes infinite, and time loses meaning. Our equations stop working. It's as if the universe hides its deepest secrets behind a wall of mathematics that refuses to be solved. Even Einstein's beautiful geometry shatters at this boundary. Scientists believe the singularity might not be a point in the ordinary sense, but something far stranger, a place where quantum mechanics and relativity must merge. But so far, they don't agree. Quantum physics describes the universe in terms of probabilities and uncertainty. Relativity describes smooth curves and certainty. Black holes are where these two realities collide, and neither wants to give ground. To understand them fully, we'd need a theory of quantum gravity, something that unites the very large and the very small. And so far, we don't have one. But nature leaves clues. Take, for example, the way black holes behave like thermodynamic systems. Stephen Hawking discovered that they're not entirely black. They emit a faint glow of radiation, now known as Hawking radiation. It's as if the black hole slowly leaks energy, evaporating over unimaginable timescales. This was a revolutionary idea. It meant that black holes weren't eternal monsters. They were dying stars with lifespans of their own. But Hawking's discovery also raised an even deeper question, one that still haunts physics today. If black holes evaporate, what happens to the information about everything they've swallowed? Quantum mechanics insists that information can never be destroyed. Yet a black hole seems to erase it completely. This is called the information paradox, and solving it might reveal the true structure of the universe itself. Some scientists believe that the information isn't lost at all, that it's somehow preserved on the event horizon, encoded in microscopic ripples of space. Others suggest that what we think of as a black hole is actually a hologram, a projection of a deeper, hidden reality. Imagine, for a moment, that our three-dimensional world is just the shadow of a two-dimensional cosmic blueprint. If true, then black holes might be the key to unlocking this hidden code, the ultimate bridge between physics and philosophy. And there's one more strange clue. When two black holes collide, they don't just vanish into darkness. They send ripples through space-time, gravitational waves, stretching and compressing reality itself. These waves were first detected in 2015, proving Einstein right once again, a century after his prediction. Each wave carries the story of a cosmic event so powerful it shakes the universe's very fabric. Listening to these waves is like hearing the heartbeat of creation, the deep, slow pulse of gravity itself. Black holes, it turns out, aren't just destroyers. They're creators, sculptors of galaxies, architects of cosmic evolution. Astronomers have found that at the center of nearly every galaxy, including our own Milky Way, lies a supermassive black hole. These giants may have played a key role in shaping the galaxies that orbit them, like gravitational conductors organizing a cosmic symphony. But this revelation only deepens the mystery. How did such immense black holes form so early in the universe's history? How could something billions of times heavier than the Sun appear when the cosmos was still young? That question leads us to the next part of our journey, into the birth of black holes themselves, and the secrets written in the earliest light of the universe. The birth of darkness. Every black hole begins with a death, the quiet, cataclysmic end of a star. But what looks like an ending to us is, in truth, a transformation. Imagine a star 10, 20, or even 100 times more massive than our Sun. For millions of years, it burns with blinding brilliance, balancing the crushing pull of gravity with the outward push of nuclear fusion. Deep within its heart, hydrogen fuses into helium, releasing immense energy that holds the star together. But one day, that balance falters. The fuel runs dry, and gravity, the same gentle force that once shaped the star, turns merciless. The star begins to collapse. Its outer layers implode inward, crashing toward the dense core. Temperatures soar to billions of degrees. The collapse triggers one of the most violent events in the universe, a supernova. For a brief moment, the dying star outshines an entire galaxy. Its outer layers are hurled into space, seeding the cosmos with heavy elements, the very ingredients that will one day form planets, oceans, and even us. But at the heart of the explosion, gravity wins. The core is crushed beyond imagination, compacting matter into a singularity. A black hole is born. From the ashes of a dying star emerges something new, something that defies comprehension. A point of infinite density where time and space themselves cease to behave normally. It's as if the universe takes everything that once was atoms, light, memory, and folds it into an invisible dot. The result isn't just a hole in space. It's a hole in the rules. But not all black holes are created equal. The smallest ones, stellar black holes, form from collapsing stars, like cosmic embers scattered across galaxies. They may weigh a few times more than our Sun, yet they fit into a sphere no larger than a city. Others, called intermediate black holes, are rarer and more mysterious, lurking in the spaces between star clusters. Then there are the true giants, supermassive black holes, weighing millions or even billions of suns. They sit at the centers of galaxies, including our own Milky Way, and their origins remain one of the most profound mysteries in astrophysics. How could something so enormous have formed so quickly, so early in the universe's history? Observations show that supermassive black holes already existed when the cosmos was less than 1 billion years old. The universe was still young, filled with newly born stars and swirling clouds of gas. And yet, somehow, these titans had already taken shape. There are theories, of course. Some scientists believe they began as the deaths of the very first generation of stars, colossal, short-lived suns made almost entirely of hydrogen. When these ancient stars collapsed, they might have created massive seed black holes that grew rapidly by consuming gas and merging with others. Another idea suggests that supermassive black holes formed not from stars at all, but directly from giant clouds of gas collapsing under their own weight, a cosmic shortcut to enormity. In the quiet darkness of the early universe, where no starlight yet burned, gravity may have pulled vast regions of gas together until they imploded, skipping the stellar phase entirely. These direct collapse black holes would have been born already massive, setting the stage for the monstrous galactic centers we see today. Over cosmic time, black holes grew, feeding on stars, dust, and entire nebulae. As they consumed, they radiated power. Their accretion disks blazed with energy, unleashing quasars, brilliant beacons visible across billions of light-years. Some of the earliest quasars shine so brightly that they outshine their host galaxies. They are cosmic lighthouses from an age when darkness still ruled the universe, each one powered by a black hole millions of times more massive than the Sun. But the growth of black holes isn't just about consumption. It's about balance. When matter falls into them, it heats up and releases powerful jets of energy, streams of plasma that can stretch for thousands of light-years. These jets can sculpt entire galaxies, blowing away gas and slowing down star formation. In this way, black holes act like regulators, keeping galaxies from growing too fast, ensuring that cosmic order doesn't spiral into chaos. They are both destroyers and caretakers, engines of both creation and control. Even our own galaxy bears their mark. At its center lies Sagittarius A*, a supermassive black hole about 4 million times the mass of the Sun. For decades, astronomers suspected its presence, watching nearby stars whirl around an invisible point with incredible speed. Then, in 2022, we finally saw it, or rather, its shadow. Using the Event Horizon Telescope, scientists captured the first image of our galaxy's heart, a glowing ring of light surrounding a dark center. It wasn't just a photograph. It was a mirror held up to the universe itself, proof that the darkness we've imagined for centuries is real. And yet, even now, new mysteries emerge. Some researchers propose that black holes might be more like gateways, cosmic bridges known as wormholes. These hypothetical tunnels could connect distant points in space and time, or even link to entirely different universes. It's a beautiful idea that what we see as an ending might actually be an opening. But so far, it remains theory, waiting for evidence. Still, one can't help but wonder. If black holes do connect different regions of spacetime, what might lie on the other side? Could the singularity, the very center of a black hole, be a portal through which the universe renews itself? Could every black hole be the seed of another cosmos, a new reality budding within the old? We may never know for sure, but one thing is certain: black holes are not merely voids. They are engines of cosmic evolution born from destruction, yet essential to creation. In the quiet language of the universe, they speak of cycles, of death feeding life, of light born from darkness. And so, as we peer deeper into the universe, we begin to see a pattern emerge. Wherever there is creation, there is also collapse. Wherever there is light, there is shadow. Perhaps the black hole is not the villain of the cosmos, but its most misunderstood architect. A reminder that even in the deepest darkness, something new is always waiting to be born. The fate of darkness. For all their power, black holes are not eternal. Though they seem to swallow everything, never releasing what they take, even they must one day fade. Deep within the equations of quantum physics lies a quiet prediction, one that transforms our view of eternity itself. It's called Hawking radiation, named after the brilliant mind that first glimpsed its possibility. In the 1970s, Stephen Hawking discovered something extraordinary. Black holes, he realized, are not completely black. Near the event horizon, where gravity bends space to its breaking point, quantum fluctuations constantly create pairs of particles, one with positive energy, one with negative. Usually, these pairs annihilate each other instantly. But if one particle falls into the black hole while the other escapes, the black hole loses a tiny bit of its mass. Over unimaginable spans of time, this slow leak of energy, Hawking radiation, causes the black hole to shrink, evaporate, and finally vanish. The universe, it seems, takes even its most indestructible creations and gives them an ending. For a supermassive black hole, this process would take far longer than the current age of the universe, trillions upon trillions of years. But smaller ones might fade sooner, glowing faintly as they evaporate in their final moments, until at last, They release one last burst of light and disappear into nothingness. It's haunting, isn't it? The idea that even the darkest things we know are not truly permanent. That the ultimate void is, in the end, temporary. When the last black hole dies, the universe will enter its quietest age. A time when no stars shine, no galaxies glow. A cosmic winter of endless stillness. But even that silence might not be the end. Some physicists wonder if the evaporation of black holes could spark new beginnings. Perhaps, in the instant a black hole dies, it gives birth to something else. A quantum ripple, a burst of energy, maybe even the spark of a new universe. In this sense, black holes could be both tombs and wombs, endings and beginnings intertwined in the same cosmic heartbeat. It's a humbling thought, that creation and destruction might be two sides of the same coin. Even more mysterious is the question of information, the blueprint of everything that ever fell into a black hole. According to quantum theory, information can never truly be destroyed. But when matter falls past the event horizon, where does its information go? Is it lost forever, or somehow encoded in the fabric of spacetime itself? For decades, this paradox haunted physicists. If information could truly vanish, it would shatter the very laws of physics. But if it survives, how? Recent research suggests that black holes might not erase information after all. They may store it subtly on their surface in faint quantum patterns too delicate to detect. Like the grooves of a cosmic record, every atom, every photon that falls in could leave an imprint, a whisper written on the edge of the abyss. If that's true, then black holes aren't prisons of oblivion. They're archives of the universe, silent libraries holding the history of everything they've consumed. And perhaps, in some unimaginable future, when the universe has gone dark and cold, those faint imprints will still exist, glowing softly in the quantum vacuum, the last memory of what once was. Black holes, then, are not just cosmic monsters. They are storytellers. They remind us that everything, even the things we cannot see, is part of a greater cycle. They are the universe's way of teaching humility, wonder, and patience. We often think of the cosmos as vast and indifferent, but maybe it isn't. Maybe, through these great dark hearts scattered across the galaxies, it speaks to us in silence. It shows us that endings are not what they seem, that every fall is a transformation, that somewhere beyond the darkness, something new is always waiting. Because that's the secret of the black hole, not what it destroys, but what it creates. And maybe, if we listen closely, we'll realize that the same principle holds true in our own lives. That even in moments of collapse, when everything feels like it's falling inward, there's a new beginning forming, unseen but inevitable. In a way, we are not so different from the stars. We live, we burn, we collapse, and in that collapse, something new takes shape. The universe within us follows the same rhythm as the one beyond. So the next time you look up at the night sky and see that faint shimmer of the Milky Way, remember, somewhere out there, at its very heart, a black hole is silently spinning, shaping the destiny of stars, guiding the flow of galaxies, and keeping the cosmic balance. It is not an end. It is a beginning we don't yet understand. The black hole's secret is not darkness. It is transformation. And maybe that's the deepest truth of all, that even the things we fear most are part of the same great pattern that keeps the universe alive. Because in the end, everything falls, only to rise again. If you enjoyed drifting through the cosmic unknown with us tonight, consider subscribing to the Sleepy Minds. There's a whole universe still waiting to be explored, quietly, beautifully, and endlessly mysterious. Thank you for watching. Until next time, sleep well and keep wondering.